on it. Okay, I want to see what you know and what you don't know. Try to hide what you don't know. Here's what we were doing last time. I want you to tell me some stuff. As you do each of these. What's up with that integral? Is that your regular run-of-the-mill integration problem?
No, it's got a discontinuity.
There we go. It's an improper integral because it's got a discontinuity in the integrand at this lower limit of integration. So this is an improper integral. That's not a good one. Because the integrand is not defined at x is 0. Everybody hear me out there on Zoom land? You have audio? Type that in the chat if you can hear me. Time. I don't put somebody to sleep out there. I'm using the camera, so it's got to be working. Okay, so we fixed this before we integrate it. We replaced that discontinuity with a letter and take the limit as whatever letter we choose goes to 0. Then we got to figure out how to integrate this. So don't skip this step right here. This is important. I'm going to take a to 0, integrate from a to 1.
It's not right.
I was just going to ask you that. It's coming in from the right because I'm looking at the interval from 0 to 1. So the interval is on the right-hand side of 0. So we're coming in from the right. Now we can go ahead and integrate. Does anybody have anything you want to try? How to integrate this thing? Take u to be the square root of x, that's right here. Because we know the derivative of the square root of x is 1 over 2 times the square root of x. So that'll take care of the one on the bottom. So I can put this 2 up here with the du. So there's a u. The 1 over the square root of x dx is the 2 du. Here's the 2 from the du. Then we're integrating e to the u. So when you integrate e to the u, you get e to the u. And in this case, u is the square root of x. So I'll kind of put 2 steps in one. Put the 1 in there for x, put the a in there for x. Then we try to take the limit of that expression as a goes to 0. So a is going to 0, that means the square root of a is also going to 0. E to the 0 is 1. So this thing is a nice finite number, 2e minus 2. That means this integral converges to that number. Any questions on that one? Yes, sir.
What would we have gotten if we didn't use the limit and just did it?
You'd have gotten the same thing.
But it wouldn't have been the right way to get the same.
That's right. Since, you know, people in the regular calculus sections can probably get away with just screwing around and going straight through and integrating. My honor students know better. So I'm going to ask you what makes this integral improper, and then you're going to tell me this, and then you're going to fix it in the correct way and tell me whether or not it converges by showing all the steps. Okay, so I'll force you to tell me why it's improper.
That makes sense.
Okay. So I might ask, what makes an integral improper? Why is this particular integral improper? Can you tell me if this integral converges or diverges? If it converges, find its value. Okay. But sometimes you're just totally wrong when you just skip the limit step. Let's see if I have one of those. I don't know if I have one of those. Let's try this problem here. Let's try this one. Let's see, I don't want to give away the secret. So this is an improper integral because the 0 again. We've got an x in the denominator. That x is not defined, or this fraction is not defined when x is 0. The integrand is not defined if x is 0. So we do the same step. Still coming from the right since we're between 0 and 1. Okay. Now what's your plan on doing that integral? Yes, sir. Take u to be x squared.
Like distribute the x.
Okay.
Take u to be x squared.
And then what's going to happen with the 2x that you get?
You get 2x squared, so that goes to 2u.
No, you get a 2x if you take u to be x squared. Let me see. Here's a suggestion is to multiply it out.
Yeah, take u to be x squared, and then you get 2x or 4x. Or I guess 2x.
That's what we're going to do with that.
You divide it out. Or am I being dumb?
So if I take u to be x squared, that kind of leaves that guy hanging too.
Okay.
It does. I don't think a double substitution is going to be a quick way to get this one through. I had it factored for a reason. Partial fractions might be quicker than trying some gymnastics to get a u to u substitution to work. And so we'll try the partial fractions. We're going to take the 1 over x times 2x plus 5. Those are both linear factors, so we can put constants on top here. On your mark, get set, go. Let's see if we can get the A and B most quickly and efficiently. Here's the values I got. Questions on those? Okay, so we can break that integral up into two integrals. It's 1/5 over x plus a negative 2/5 over 2x plus 5. When we do both of these integrals, we'll get logarithms, but the second one's going to spit out another factor of a half, because if u is equal to 2x plus 5, the du is 2 times dx. So we'll get a 1 over u with another 1/2. So this becomes 1/5 times the natural log of x. I don't need the absolute value bar since I'm in a positive range. And this becomes, once I multiply this 2/5 times the 1/2, that's going to be another 1/5. And that's going to be a natural log of 2x plus 5. Then we evaluate that from a to 1. So when I multiply out there, I get a negative 1/5. Now I'm going to put the 1 in there. And then the a. So I'm going to get 1/5 natural log of 1 minus 1/5 natural log of, oh, what is that, a 7? And then we subtract 1/5 natural log of a minus 1/5 natural log of 2a plus 5. Does anybody know what the natural log of 1 is? It is 0. So that's a constant. I can pull it out here. Okay. We're inside these parentheses. I'm going to pull out the 1/5. And I have a natural log of a minus the natural log of 2a plus 5. Tell me what your thoughts on that limit inside the parentheses as a goes to 0 from the right. Remember a logarithm? What's it look like? A logarithm does something like this. This is 1. So as a goes to 0, the natural log of x goes to minus infinity. So this is going to minus infinity, right? A is going to 0. So this is going to the natural log of 5. So I get a negative 1/5 natural log of 7 minus, what I say, this is going to a minus infinity, but that one over there is going to the natural log of 5. And so this is going to pull it all the way to plus infinity, right? So this integral diverges. So we've seen one that converged and one that diverged. Now let's try this one. 4 to infinity of 1 over x minus 2 times x minus 3. And you start by telling me that this is an improper integral because, yeah, the infinity, we can't integrating to infinity. So this is what makes this improper integral. So we put a letter up there and we run the limit as that letter goes to infinity. I'll use a big M. Integrate from 4 to M. And it looks like you get to do partial fractions again, right? Let's go, whip it out.
Wait, so even though those technically have discontinuities.
But there's not a discontinuity between 4 and M. This one's continuous at x is 2.
Oh,
So it's outside that range, and this one's at x is 3. So that's a good point.
I'm blind, yes.
Always look for that as well. But 2 and 3 are not in the interval from 4 to M, so we're okay on that kind of discontinuity.
Can you have a type line?
You can. You can.
Oh,
It's going to set up a couple limits.
oh boy.
So for instance, if I were integrating from 3 to M, then I would have an integral, say, from 3 to 0 and 0 to M, and then run 2 different limits.
Can't wait for that bonus question.
Okay, so you're doing partial fractions again. I hope it's just as fast for you as it is for me, that you recognize when to do it and that you actually pull it off. So we multiply here. So x is equal to 2 is going to give us a. So a is -1. X is equal to 3 is going to give us b. B is a +1. So now let's break up our integral. So a was a -1. And b was a +1. And those are both your run-of-the-mill logarithms. Bigger. So I get minus the natural log of x minus 2 plus the natural log of x minus 3, evaluated from 4 to m. So I have minus the natural log of m minus 2 plus the natural log of m minus 3. Now we're putting the 4 in there. This one's going to give me the natural log of 1, and you guys already told me that's 0. So this is going to give me minus the natural log of 2. And change that to plus the natural log of 2. So here's the difference between this problem and the last one. M's going to infinity. So we're looking at the other tail of the logarithm graph. Both of these are growing functions. So they're both getting infinitely large. But this one's got the minus sign. So this one's behaving like a minus infinity. And this one's behaving like a plus infinity. What the heck does that mean?
0.
It's not 0. That's one of our indeterminate forms. Right? Some of our indeterminate forms that we had back in chapter 4. the ones that we encountered in chapter 2 were of the 0 over 0 or infinity over infinity, which implies some sort of common factor that we can cancel. Or if there isn't a factoring eligibility, we can use L'Hopital's rule. But then we had several other indeterminate forms that were more of the algebraic type, and this is one of them. So other indeterminate forms are the one that we have here, infinity minus infinity. Then we had something of the form infinity times 0, 1 to the infinity, infinity to the 0, and I think 0 to the infinity maybe. Those are all indeterminate forms. And what we have to do is to algebraically change them from these forms so that we have some version of a fraction. Well, I've got logarithms, and one is subtracted from the other, so I can make a fraction. What do you know about a log property with subtraction? Division. You divide, you make one logarithm and divide the positive over the minus. So I'm going to use the fact that the natural log of A minus the natural log of B is the natural log of A divided by B. That one's got the plus, so that's on top, that one's on the bottom. So now I'm taking the limit as m goes to infinity of the natural log of m minus 3 over m minus 2. Neither of those is negative in that range, so I can go ahead and get rid of the absolute value bars. Now you take the limit as m goes to infinity by moving inside those parentheses. We can jump over the logarithm, go inside the function, and take the limit in here. What's the limit of m minus 3 over m minus 2 as m goes to infinity? Okay, so what does infinity over infinity tell you can do with L'Hopital's rule? Derivative of the top divided by the derivative of the bottom. The derivative of each of these is 1. So this results in a 1, right? Or we had that quick eyeball way, if the same degree, top and bottom, then you just take the coefficients. So the coefficients of each of these is a 1. So the stuff inside the parentheses goes to 1 as m goes to infinity. So I get the natural log of 1 right there. This particular integral converges to the natural log of 2. So I wanted to do that to show you the difference between here when only one of them was infinitely large and there when both of them were infinitely large, but one of them was minus. If they're both positive, infinity plus infinity goes to infinity. But infinity minus infinity is indeterminate. Okay? Have you seen enough of those? Do you want to ask me any questions about anything from 7.7? Yes, sir.
So the minus infinity plus the infinity, in this case, ends up being 0.
In this case, it did. It doesn't
But it
always.
doesn't always do
Yeah, I
that.
can find some. I'll get you some examples today where they're not. So it's really hard to read. Maybe it's because I don't have glasses. Oh well. So I've got one more I want to show you. Who remembers how to find the length of an arc of a curve?
It's in there.
It's in there, it's a formula. Y is equal to f of x, the length of the arc from A to B.
Square root of 1 plus the derivative.
1 plus the derivative squared, and then you integrate that from A to B. Hell yeah. Okay, does anybody know what the unit circle is? What is it?
It's a circle.
Unit means what? What is
Circle of angles.
what is the radius of the unit circle?
One.
One. So it's not just a circle, it's the circle. It's the king of all circles. X squared plus y squared is equal to 1. So the radius is 1. What's the arc length all the way around that circle? 2 pi. 2 pi r, 2 pi times 1. But let's take the equation. X squared plus y squared is equal to 1 and find the length all the way around the circle using our arc length formula.
Is this a new
Righteous.
section?
No, this is the same. I know, you're dying to get out of this section. Reagan wanted to see something where both endpoints were screwy, so I've got one, but not.
It seems I have made an error.
Okay, so the unit circle has equation x squared plus y squared is equal to 1. So we're going to find, using our arc length formula, find using that formula the length or the circumference of this circle. So here should be x squared plus y squared is equal to 1. So we need to get first y as a function of x, and then take its derivative. So take that equation x squared plus y squared is 1 and solve for y in terms of x. So we start by saying y squared is 1 minus x squared. And now there are two roots here. The positive square root is the top half of the circle. The negative square root is the bottom half of the circle. But don't you agree that the length around the top half is the same as the length around the bottom half? So let's use symmetry, keep the positive square root, and just double our formula. So our arc length is going to be twice the integral of the square root of 1 plus, now I need your derivative. So we're going to look at the derivative of y is equal to 1 minus x squared to the positive 1/2. Bring the power down, raise that to 1 power less, multiply by the derivative of what's inside. And that goes in here. And then, oops, I got to square it as well. So put the derivative in here. I need wider parentheses then. 1/2, 1 minus x squared to the negative 1/2 times negative 2x. And what are the limits on my integral? What's the range on the x's? For the top half of the circle. -1 to 1. All right. Now let's simplify that derivative. Let's see, I can take half of the 2x and get an x, square that and get an x squared. Get rid of the minus sign since we're squaring. So I got an x squared. This is going to go on the bottom with a positive power, and then I'm going to square it. So I'm just going to get a 1 minus x squared there on the bottom. That's all the squaring. So I'm open to suggestions again. We need to try to integrate that.
It's not negative x squared.
We're squaring it. Negative times negative is positive.
Should we make one an even, like a common denominator?
Yeah, let's get a common denominator. So let's treat this as 1 minus x squared over 1 minus x squared. write them as a single fraction. So that's kind of nice. The x squareds add each other out, leave me with just a 1 on top. Both are under the square root sign, but the square root of 1 is just 1. So I'm going to go here. But we're going to stop for a minute and recognize that we've got an improper integral. At both endpoints, right? 1 minus x squared is going to be 0 when x is 1 and negative 1. So this is a big time improper integral because integrand is not defined at x is plus or minus 1. So we got to fix it before we try to integrate it. First, we're going to write it as two integrals, from -1 to 0, 0 to 1. And then we're going to put letters where the -1 and the 1 are. First, we're going to write that as -1 to 0. And then we're going to write that as the integral from 0 to 1. And now I'm going to put, say, an A and a B where the 1 and the -1 are. Let's move over here. Here's what we have to compute. Let's say the limit as a goes to -1, from a to 0, plus the limit as b goes to +1, from 0 to b, this interval covers a to 0, so I'm coming in toward the right. This interval covers 0 to b, so I'm coming in from the left. And then somebody already mentioned what that integral is. Who said it? What is it? What's the integral of 1 over the square root of 1 minus x squared? No? You recognize that integral?
Someone said arc sign.
It is an arc sign. It is an arc sign. This is a 1, so it's just the arc sign of x in both of those cases. So we got a 2 here. We got the limit as a goes to -1 from the right. This is going to be the arc sign of x from a to 0, plus the limit as b goes to 1 from the left of the arc sign of x from 0 to b. Okay, you think, the suspense is killing me. I can't wait to see what this is going to be. But we already know the answer, right? The length all the way around the circle is 2 pi. So somehow that represents 2 pi. We're going to put a 0 in for x and then an a. So I have the arc sign of 0 minus the arc sign of a, plus the limit as b goes to 1 from the left, the arc sign of b minus the arc sign of 0. Do you agree that the arc sign of 0 is 0? The arc sign is looking for an angle that I would take the sine of to get that 0. The sine of 0 is 0. So I ran out of room, so I went ahead and gave that away. So here we are. A is going to -1, So I'm kind of looking at what is the arc sine of -1. What angle do we take the sine of to get a -1? Can't be 3 pi over 2 because the arc sine is only defined in quadrant 4 to quadrant 1 in that way. So instead of calling it 3 pi over 2, it has to be negative pi over 2. So this is a negative pi over 2. And with that sign right there, makes it a positive pi over 2. Over here, I'm going to 1, so this gives me the arc sine of 1. And that would be positive pi over 2. And there's your 2 pi. So that was potentially your bonus for the exam on Tuesday. And I just showed it to you, so I have to think of something better.
Or just keep
What?
See if we remember it.
Just remove our memories.
Oh, we have a test for a week.
Yeah, we haven't tested in 1 week. Make it what? 1.5. We gotta get her done. I think we're at midterm. I gotta turn in midterm grades for y'all. I always forget it anyway. I always think, oh yeah, turn in midterm grades. Oh yeah, turn in midterm grades. Oh darn, I forgot midterm grades were due yesterday.
This entire midterm is just gonna be integrals. It's kind of funny.
I could put section 8.1 on there.
Is that sequence of the series?
We're gonna start sequences right now.
Oh, no. Let's do
You
it.
just want chapter 7 on this test?
We will be more,
I'm sorry?
if it's just chapter 7, it has to do all the intervals you want.
That's right. That's right. Here's what I kind of roughly thought about doing is that in section 7.7, I've got to kind of isolate those so that you can tell me, I can't just squeeze them in with the rest of them. But maybe have a couple of problems from section 7.7 before you can tell me why it's improper and then show me whether it converges or not. And then maybe I'll give you a page of integrals, maybe 12, 15 integrals and say do any 10. So that way you get to pick out which ones you think are the easy ones and which ones you think you want to avoid. How's that sound? Can you do that in an hour and 20 minutes?
That's solid stuff.
Solid stuff. Oh, I just got complimented on how well I do my job.
Could we do like a speed integral competition to see who can get more extra credit?
Oh.
That'd be funny.
Listen, I can do math, I just can't do it fast.
Actually, that sounds funny though, like doing a math challenge, like a math club challenge where you're just trying to integrate really fast.
Do it really fast. Well, we do want to practice safe integration. If we go fast, we make mistakes. Okay, so I think my other class would agree that they only want chapter 7 on this test, even though I will start chapter 8. So our test is Tuesday.
I thought you were spelling Tuesday.
Me too.
All right, now somebody's got to add 7 to 16. Tuesday, March 23rd, covers chapter 7. I'll put a review up on Blackboard after I turn in your midterm grades. No, I don't know. We're not putting it in probably today. So it shouldn't be too hard. We've been integrating like crazy. And there'll be a mixture of ones that are basic, easy things like that, right? And then some that you have to do a little bit more steps. And your job is to get it done in the right time period by choosing the shortcuts and not doing everything with the trig substitution. Okay, so I probably better start section 8.1. So let's see, in chapter 8, we have like 7 sections, maybe 8 sections in chapter 8. Then we got 4 sections in chapter 9. So usually my third test just covers chapter 8, and then the chapter 9 stuff will be included on the final. So We're wrapping it up. In section 8.1, we're looking at sequences. And here are some examples of sequences. We're looking at infinite sequences. Let's see, 3, 7, 11, 15, there's a little gap there. 8, 4, 2, 1. Um, 1, negative 1, 1, negative 1, 1, 1, 2, 3, 5, 8. A sequence is a list of numbers that may or may not exhibit a definitive pattern. In calculus, we describe a sequence as being a function that pairs the set of counting numbers to a real number. The counting numbers count the position it's in. First term, second term, third term, fourth term. So we denote a sequence in terms of subscripts. I use lowercase letters to denote a sequence. So a sequence is a function that pairs the set of counting numbers to a set of real numbers. So when the input is 1, the output is A1. The input is a 2, the output is A2. We denote the sequence by putting a general formula in here that describes what each of those look like. And we put them in the cute little brackets to let you know we're talking about a sequence. Are you able to predict, say, the next 4 terms of each of these patterns that I put up here? What are the next 4 terms here? Because all we're doing each time is we're adding 4 to the previous term to get to the next term. That type of sequence where you just always add the same number all the way down the line to get the next term is called an arithmetic sequence. Arithmetic sequence, you always add the same number to get to the next one. So my x's represent the counting numbers and my y's are the outputs. Each time I increase x by 1, I go up by 4, 1 to 4, 1 to 4. So this describes a linear relationship if I were to plot this on an xy plane. I'll go ahead and do it. Here's my xy plane. I only need my counting numbers. So 1, 2, 3, 4. So that's the ends, and these are the terms. So my first term is a 3. So let's say that that's a 3. Then I'm gonna go up by 4 to hit 7. So if that's 3, that's up 4. So now that's 7. Term number 2 is a 7. We go up 4. Term number 3 is an 11. And then up 4, term number 4 is a 15. So arithmetic sequences describe things that either grow or decrease linearly. Okay, can you tell me the next 3 terms in example 2? Next 4 terms, sorry.
Half. 1, 8, 16.
And you're dividing by 2 each time, or multiplying by a half? Where the terms are generated by multiplying by a fixed number to get the next number, you have something called a geometric sequence. You're multiplying by 1/2 to get the next term. And so if I were to plot this, I would have 8, and then my next integer value is 4, and then 2, and then 1, and then a half, and a 1/4. If I did this forever and ever and ever, eventually, how big are the terms? We're getting real close to 0, right? But if I did this forever and ever and ever, the terms continue to grow without bound. So that's important. This particular sequence has a limit as n goes to infinity of 0. As n goes to infinity, this sequence goes to infinity. A sequence is said to converge if it has a limit. This one converges to 0. So this sequence converges to 0. I can probably describe this sequence in terms of a general formula. These are all looking like powers of 2 or dividing by powers of 2. So how about I write this like say n is a set of counting numbers. If n is 1, I have 2 to the 0 on the bottom. 2 to the 0 is just 1, so that gives me 8. If n is 2, I have 2 to the first power, so 8 divided by 2 gives me the 4. If n is 3, 3 minus 1 is 2, so I'm dividing by 4. 8 divided by 4 is 2. So here's an example of something called a general formula for this sequence. We can probably figure out a general formula for this sequence in number 1. The general formula tells you how to get any term by whatever the input variable is, which in this case is n. N is a set of inputs, and then the ANs are the outputs. So here I can tell you from this formula what the 15th term will be. It'll be 8 divided by 2 to the 14th power. Can you come up with a formula to give you the nth term here? Let's see what we do to the 3 to get to each term. Here I know 3 plus 4 is 7. Well, how do I get from 3 to 11?
3 plus 2 times 4?
3 plus 2 times 4. And to the third one? 3 plus 3 times 4. Actually, this is the 4th term, right? That's the 3rd term, and that's the 2nd term. So suppose I want to get to the nth term.
3 plus 4n.
There's the term number compared to the number of multiples. So why don't we go n minus 1 times 4? So we're looking at a sequence converges if it has a limit. So let me write that down. A sequence is said to converge if it has a limit. And I mean a limit as the counter n goes to infinity. So we take the limit as n goes to infinity of the general term and get some number L that the sequence converges to. So that once we're past a certain point, all of the values of the sequence look like that. So if this is a sequence in general, there's a set of counting numbers, and there's a set of terms. Maybe, let's see, let me mark this off. Here's some integer values. And then let's just kind of break up the number line. So suppose I got a term, maybe it goes up a little bit, comes back down. But if after a while, all of the terms kind of hang out in the same spot, that spot being the number L, as we pass some very large number, then we say that the sequence has a limit of L if all of those terms live within a teeny, teeny, tiny interval around L. So it's easy to predict in number 3 the next 4 terms. So this sequence does something like this. It's 1, and it's negative 1, and it's 1, and it's negative 1, and so on. Do you think that thing has a limit? Not a chance, huh? Because it bounces back and forth. If I were to write a formula for this, maybe I can say that that is negative 1 raised to the n plus 1.
Isn't that just a cosine graph or a sine graph?
Well, it's not connected, it's just individual points.
Oh, okay.
So it's a
okay.
discrete picture, not a continuous picture. And so you can see that this thing, as n goes to infinity, does not exist. It doesn't equal 1, doesn't equal to negative 1. It doesn't exist because of the oscillation. So we say that the ones whose limits become infinitely large, or who has no limit, that these two sequences are said to diverge. This diverges because as n goes to infinity, the general term goes to infinity. This diverges because there's not a limit of the general term. The next one keeps growing forever and ever and ever as well. Have you seen the sequence in number 4 before?
Fibonacci.
That's a Fibonacci sequence. You get the next term by adding the first 2 terms together. So I got to spot you the first 2 terms, then you add them to get the next one. Add the previous 2 terms to get the next one. Add the previous 2 terms to get the next one. So I'm not able to write a general formula for that, but I can write something called a recursion formula. That the nth term is the sum of the 2 previous terms.
terms, like, has to be given.
These two have to be given. If I really want this, my counter to start at, I can't start this counter at 1 because then I get a negative subscript. So let's start this counter at 2 or 3. So this is called a recursive formula. A general formula gives you the term only in terms of the counter n. A recursive formula has to describe what's happening to previous terms. Sometimes kind of hard to come up with a general formula. But what I'm going to do next is give you some sequences in terms of the general formula. I'm going to ask you to write out the first 4 terms and then tell me if the sequence converges or not by taking the limit as n goes to infinity. Red's hard to read. Black is hard to read. So I'm going to rub this out. Okay, so these are following examples. They write out the first few terms. I don't know. We'll see if they get to be a pain in the neck of each sequence. Then determine if the sequence converges or diverges. There's the general term for your first one. Call out the first, say, 4 terms.
1/2,
1/2,
2/3, 3/4, 4/5.
there you go. And the handy thing about this formula given in terms of n is you can tell me what the 100th term is without having to write down the first 99 of them. What's the 100th term? 100 over 101. So as you keep running this out, those values are getting closer and closer and closer to what? To 1. This sequence converges to 1 because I'm going to take the limit as n goes to infinity of n over n plus 1. So since there's an n in each, the numerator and denominator, this behaves like infinity over infinity. And so you can use L'Hopital's rule. Let me remind you of L'Hopital's rule. It says, you take the limit as x goes to a, where a can be a number or a can be infinity, of something that looks like f of x over g of x, if that limit has the form of infinity over infinity infinity for 0 over 0, and the limit as x goes to a of f prime of x over g prime of x is equal to L, then the limit as x goes to a of f of x over g of x is also L. In other words, if you have the form infinity over infinity or 0 over 0, and you're able to take the limit by taking the limit of the derivative of the top of the derivative of the bottom and get a limit, then that's the limit of the original expression. So the important thing is that this is not the quotient rule, that L'Hopital's rule comes from looking at the tangent line approximation to the graph. Right? The equation of a tangent line looks like y is equal to the y value at the point plus the derivative at that point times the x minus the point. So if we did that here, take the derivative of the top and the derivative of the bottom, we just get a 1, right? 1 on top, 1 on the bottom. But we also had the rule that if you're taking the limit of rational expressions and the degree on the top is equal to the degree on the bottom, L'Hopital's rule will always give us the ratio of the coefficients. Just look at the highest power. And if they're the same, just take the numbers in front of both. You remember doing that? And if they're not the same, what if it's bigger degree on the bottom? The degree is bigger on the bottom, then the limit will go to 0. You remember that? It grows bottom heavy. But if you did one application of L'Hopital's rule, you'll see that the derivative of top is 4. The derivative of bottom is 2n plus 1. So as n goes to infinity, I have 4 divided by something that's getting infinitely large. Let's write out the first few terms anyway. Let's see, if n is 1, I get a 6 on top. If n is 1, I get 7, 8, 9 on the bottom. 6 9ths or 2/3. If n is 2, I get a 10 on top. 4 plus 2 is 6. 6 plus 7 is 13. Now n is 3, I got 12, 14 on top. And 4, 16, 27 on the bottom. Slowly but surely, those are getting closer to 0. Right, that first number is about 2/3. The last third number there is about 1/2. So they're slowly, slowly, slowly going to 0. Okay. Without glasses. Stuck without glasses. What the heck am I doing without glasses? There's my papers over there. So the terms are easy. E to the negative 1, e to the negative 2, e to the negative 3, e to the negative 4, blah, 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 blah.
0?
Should be going to 0. Because?
I mean, the negative exponent is just a denominator.
That's right. E to the minus n is the same thing as saying 1 over e to the n. And then as n goes to infinity, e is a growing function, so e to the infinity gets infinitely large. 1 divided by infinity is going to go to 0. So this converges to 0. So all three of these converge so far. This one converges to 1. This one converges to 0. And this one converges to 0.
Doesn't the first one give you a 0 in the denominator?
So we'll start at n is bigger than 1. How about that? Start your counter at 2. We start at 2, we have 2 divided by the natural log of 2, 3 divided by the natural log of 3, 4 divided by the natural log of 4, so on. Well, you can try L'Hopital's rule, right? Because both n and the natural log of n get infinitely large. We have infinity over infinity. I'll help you. The derivative at the top is 1. Your turn.
Over n on the bottom.
So when I simplify that, I'm doing this, right? So this one's getting infinitely large. This one diverges. Not many things grow slower than the natural log of n, right? Let's look at something called our tower of powers. Log of n is way the heck down here. It's very slow growing. It grows even slower than, say, the square root of n, which square root of n grows slower than n. N grows slower than n squared. N squared grows slower than n cubed. And so on. As the powers increase, they grow faster. So something that grows faster than n cubed, I don't know, which grows faster, n cubed or 3 to the n? So if I had which is faster? 2 to the n grows faster, it doubles each time, right? N squared over 2 to the n, that looks like 1 over 2, 4 over 4, and it's 3, 3 squared is 9, 2 cubed is 8. 4 squared is 16, 2 to the 4th is 16. Oops, what did I just do? 1, 2, 3, 4, 4 squared is 16, 2 to the 4th is 16. 5 squared is 25, 2 to the 5th is 32. Yes? So I take the limit as n goes to infinity, of n squared over 2 to the n. You have to remember how to take the derivative of 2 to the n. I know how to take the derivative of n squared. Who remembers how to take the derivative of 2 to the n? Go ahead.
Would you turn it into a natural one?
2 to the n, not a natural log, kind of. E to the natural log of 2 to the n is the same as 2 to the n, right? So this n can come in front. E to the n natural log of 2. So the derivative is itself times the derivative of the exponent. So I get itself here, e to the n natural log of 2 times the natural log of 2. So which grows faster, 2 to the n or e to the n? Or 2 times n or e to the n? E to the n grows much faster, so the bottom is growing faster than the numerator. If you keep doing L'Hopital's rule, your next derivative is a constant, and your next derivative here is going to have another e to the n. So this one's bottom heavy, the limit is 0. Exponential functions grow faster than power functions. So 2 to the n grows slower than 3 to the n. Somewhere in here is e. E is between 2 and 3. No, 2.7? Yeah, e to the n, 3 to the n, 10 to the n. You know what this means? What does it mean? It's n minus 1, n minus 2, and so on. Those grow faster than those. N to the n probably grows even faster, right? So, in other words, if you read up here, if your denominator is bigger in terms of its growth speed than the numerator, then your limit will be 0. But if you've got that faster growing term on top than you have on the bottom, then your limit is going to be infinitely large. So those describe how fast things grow. So without writing the first few terms, tell me if this sequence converges or not. I've lost what number I'm on. What's the limit of that one going to be?
30.
Because?
You have n to the 1/2 on top, and then the highest power on the one ends into 1/3.
Yep. Highest power up here is into the 1/2. Highest power down here is into the 1/3. So it's top heavy. It says that that limit is going to grow without bound. Slowly, but it grows. And you want to know that because doing L'Hopital's rule of this is just impossible. You're never going to come out with something nice and pretty. You just kind of eyeball it and see where the biggest power is, or where the faster growing term is. That will be 0. You think it's 0 because the first term gets infinitely large and the second one gets infinitely large and you're subtracting? Yeah, but we're taking the square root of it, so doesn't that tamper it? So this behaves like n to the first power, that behaves like n to the first power. This is an indeterminate form. As is 0 times infinity. Even though you might want to think 0 times infinity, no, that should be 0. Not always. It's indeterminate. These two forms require you to do some algebra so that you can make a fraction and look at our tower of power. How do I make a fraction out of the difference of two terms? One? Yeah. Let's go. Got the common denominator, made a fraction. I still have infinity minus infinity. Over 1.
Could you multiply 2 on that n over b?
By what?
N over by each one.
Close.
Conjugate.
Conjugates.
I was guessing, so please don't.
You're not guessing. You were taught that in an earlier class.
Okay.
One of the tricks in cleaning up radical signs is to multiply by the conjugate. The conjugate of the difference between two terms is the same, but with the sign changed in here. So I'm going to multiply top and bottom by the sum of those two. We've done all of this back when you were in chapter 4 in calculus 1. Perhaps by that time we were all doing it online. So why do we choose that? What happens when you multiply those two numerators together? We get rid of the square root sign, right?
Yeah.
Because this is the difference of squares. It multiplies like a minus b times a plus b, which gives us the first term squared minus the last term squared and no middle term. Well, my first term squared, oops, I'm out of time, doesn't have the square root sign, and my last term squared is just an n squared. So I get n squared plus 5n minus n squared over this. We're almost done. So I lose the n squareds. I get a 5n over this. Close, but look at the powers. The numerator acts like degree 1. What about the denominator?
Degree 1.
Acts like degree 1 as well. The highest power under here is an n squared, but it's under the radical sign. So that behaves like n, that behaves like n, and that does. So we can get the ratio of the coefficients. So I get a 5 here, a 1, a square root of 1 there, and a 1 there. So this sequence converges to 5 halves. Aren't you glad we went over time to show you that? Okay, I do have a web workup on section 8.1. I will put up a review for your test on 1 week from today. We'll review a bit. Oh, I've got some papers up here. Those of you that turned into paper homework, come swap with me. I've lost my glasses, so I can't read these tiny names. Just like yours. Thank you. I didn't see Lucas today. Grace is here. Come on, paper. Don't trip over my wires. Oops, I didn't flip that off. there's any sound on it.